So in today's session we'll start with the timing arcs. So the timing arcs are divided into two parts. One is called cell arc and another is net arc. So let us see the definition of timing arc first. So in static timing analysis, timing arcs are the fundamental concepts used to model the behavior of a digital circuit. So they represent the relation between the input and the output signal transitions in a logic cell or a block of the circuit. So the timing arcs are essential for determining the delay, setup and hold times as well as overall timing behavior of the design. So basically, these timing arcs are defined as a part transfers by a signal from input pin of a cell to its output pin. For example, uh, this is our cell, which is AND gate. Okay, so these are our input cells. Sorry, these are our input side, and this is our output side. Okay, so the timing arc is the part transfers by our input to output. So how the input signal is traveling from this input to output. This is our input signal. This signal is traveling from input side of this cell to this output side. So this path is called a timing arc. Okay. So basically this path is called a cell arc. Okay. This is called a cell arc. So uh, for a cell there may be more than one timing arc, and by the information of different timing arcs that exist for a cell we can calculate the delay for each path. That will helps in timing analysis and optimization. So this is basically a combinational circuit. I hope you are aware of this combinational circuit. Basically it is a logic gate, right? So sorry, this is a logic gate. So for this, it is having two paths. So these are my two inputs and this is my output, right? So the signal may travel from path A to Y, or it may also travel from path B to Y. So these are the timing arcs for this particular cell. Okay. So we have seen those are divided into two types, right? First one is cell arc, and next type of timing arc is called net arc. Okay, next is called net arc. So we will see one by one what is meant by cell arc and what is meant by net arc now. So a cell arc is defined as a path transversed by a signal from input or source pin of a cell to the output or sink pin of the cell. Okay, so cell arc means the path traveled by a signal from input of a cell to the output, or we will call the output as sink. We will call input as source also. Okay, from input or source to the output or sink pin of the cell. Okay, sink pin of the cell. So let's say this is our cell. It may be a combinational circuit or it may be a sequential circuit. It is a cell which is a black box, so which has some particular number of inputs and particular number of outputs like this. So the path traveled by the signal from input pin to the output pin is called a arc. It's called a timing arc or cell arc. Okay. Since we are considering a cell, it is called as a cell arc. So the path traveled by the signal from input pin of a cell or source pin of a cell to the output pin or sink pin of a cell is called a timing arc or cell arc. Okay. So these cell arcs are again divided into two parts. One is called combinational arc and another is sequential arc. Okay. First of all, let me tell me whether the definition of cell arc and explanation of cell arc is it clear? This is clear, right? Shall we move forward?
Yes.
Yeah. Now, coming to the combinational arc, so the path transfers by a signal from input to output pin of a combinational cell. Okay. So if there is a combinational circuit, let's say this is my combinational circuit. So the path traveled by my input signal. So the path traveled by my signal from input side to my output side is called combinational arc. Okay. Whereas in case of sequential path, so we have another arc which is called as sequential arc. So in this case, the path transfers by a signal from clock pin to the output pin or clock pin to the input pin of a sequential cell. Okay. So let me explain this with the help of a T flip flop. So let us. This is my T flip flop. This is my outputs, and since it is a flip flop, we have a clock signal, right? So it may be any type of signal, positive edge clock or negative edge clock, like that. This is my T flip flop which is having clock. This is my input. These are my outputs, right? So here we are giving our input. So the sequential arc is the path transfers transfers by a signal from clock pin, or so the path travel by our input signal from clock pin to the input pin. Wait a minute. So in case of the sequential arc, the signal, the path traveled by the signal from clock pin to the output pin. So the signal traveled by the path, the signal travel in the path from clock to output, or from the input to, from the clock pin to the input pin, either from clock pin to the output pin or clock pin to the input pin. So these two paths are called as sequential arcs. Okay? Sequential arcs. So the path traveled by signal from clock pin to the output pin or the clock pin to the input pin of a sequential cell. So there are two timing checks also in the sequential arc. One is called a setup time check, which is done between the clock and input pin, and another is called hold check, which is done between the input and input clock and input of a sequential cell. Okay, so we will discuss what is this setup time check and hold time check. And between the clock pin and the output pin, sequential delay arc exists. So we have different types of checks like setup time check, hold time check, like that we will see in our upcoming sessions. So for now, remember this, what is the paths available in this. Okay, so between the clock to input, the path is called sequential arc, or it is also known as timing check arc. Okay, timing check arc. Here we will check setup time, setup check, and hold check. So this setup check and hold check will be performed between the clock and the input. Okay, we'll see how we are checking that. And one more is delay check between clock and the output. Between the clock and the output, this is called delay check. Is it clear? Shall we move forward? So uses of this timing arcs is, so in HTA the tool analyzes the timing arcs to compute the delays through the circuit and ensure that all timing constraints are met. So uh, the propagation delay calculation will be performed by the tool, and the setup time and hold time analysis will be performed on slack calculation. Clock skew analysis will be done by the HTA tool using this timing arcs. So before discussing about this particular calculations, we will move forward, and after completing the definition discussion about this setup time, hold time, and slew, slack, all this, after this we'll come back to this and we will see what are this and how that tool is performing. Okay, now let's discuss what is meant by net arc. So the arc between the output pin of a cell and the input pin of another cell is called a net arcs or net. So let me draw a circuit. So let's say this is our NAND gate, and this is our AND gate. Okay, so these are my inputs A and B, and this is my Y. So the arc between the output pin of a cell and the input pin of another cell. So this is basically a cell, right? This is a combinational cell, and this is also combinational cell. So here, the path for the signals from input pin to the output pin for this particular cell is called cell arc. So this is my cell arc, right? This is my cell arc. Okay. So this is called net arc. The arc between the output pin of a particular cell and the input pin of the another cell. The output pin of first cell and the input pin of another cell. The part between the output pin of first cell and input pin of second cell is called net arc. So this is called as net arc. Is it clear? Simple definition. Is it clear? I hope this is clear. Right. Now let's discuss about another topic which is called uniqueness. So, coming to this uniqueness, when an input is applied at the input pin, there is a change in the value of the output, right? So, uniqueness is defined as a sense of the change in the output with respect the input applied and the time it takes to reflect the changes. Okay. So, let's say this is our particular black box. So, it may be made up of any combinational circuit, or it may be made up of any sequential circuit, right? So these are our inputs, and this is my output. Now, uniqueness is defined as a sense of change in the output with respect to input applied. So whatever we are applying as the input, the signal. So we will see in this uniqueness how the output is changing with respect to the input. Okay. So with examples we will discuss what is this uniqueness. So basically we have three types of uniqueness. First one is positive uniqueness. Positive uniqueness. So let's see what is this positive uniqueness. So when the input goes from low to high, it will cause the output to change from low to high and vice versa. For example, if we have a buffer, the best example is buffer. So let us see this buffer. So what is buffer? What it does? So this is the symbol for buffer. This is my input and this is my output, right? So whatever input I apply, so if I apply 0, the output will be giving 0, or if I apply 1, I will get output as 1. So this is the behavior of buffer, right? So by timing diagram, let's see. So this is at t is equal to 0, t is equal to 5 nanoseconds. Okay, this is my input and this is my output of my buffer. So my input signal is changing at t is equal to 5 nanoseconds, right? Like this it is changing. So at output, what can I see? The output also follows the input signal, right? In case of buffer, if we apply 0, output will be equal to 0, and if we apply 1, the output will be equal to 1. Is it clear? So here the output is changing with respect to the input. Okay, so the output is changing with respect to input, so it is called as a positive uniqueness. Positive uniqueness. Is it clear?
Yes. Yes.
Second one is negative uniqueness. Negative uniqueness. Any idea what is this negative uniqueness? Opposite to positive uniqueness. What can be? What can it be? So
Not gate.
yeah, yes. So in the case of negative uniqueness, when the input goes from low to high, low to high, then the output will be going from high to low. Okay. So this is negative uniqueness. The best example is not gate. Okay. Let's see the not gate. Yeah. So this is at t is equal to 0. This is my input, and this is at t is equal to 0. This is my output, right? And t is equal to 5. T is equal to 5. Okay. So here uh, I'm changing my, okay. So initially it is 1 and t is equal to 5 nanoseconds. I'm changing my input to 0. What happens here? At the output, I can see the output is changing from 0 to 1 at t is equal to 5 nanoseconds, right? Like this, the output changes. So this is called negative uniqueness. Is it clear?
Yes.
Yeah. And there is one more type of uniqueness which is called non-unit. Wait a minute, let me add some more slides. Yeah. So we have one more type of uniqueness which is called as non-unit. Can you guess the definition for this? So in this case, the output does not depend upon the does not depend upon the transition of input signal. Transition of input signal. Okay. So the output transition does not depend on the input but also depends on the other input supplied. Okay. So here the output transition does not depend on only one input but also depends on other inputs. Right. So for example, we can take we can take the example of XOR gate. In case of XOR gate, if we have inputs A and B and output Y, 0 0 0 1 1 0 1 1, this is our my truth table, right? So tell me whether output is depending upon only one input or it is depending upon both the inputs. So in this case it is 0 1 1 0. So in this case, the output depending upon only one input, one single input, or it is dependent upon both the inputs?
Both the inputs.
Yes. So that's why this type of uniqueness is called non-unit. Okay. So the output of this particular gate is not dependent upon one input, only one input transition. It depends upon other inputs also. It depends upon other inputs also. Is it clear?
Yes.
So these are the three types of uniqueness. So the significance of uniqueness is uniqueness only tells that how the output is sensitive to the applied input. Okay. So with the help of the uniqueness, we can find out how the output is sensitive to applied input, and the cell delay depends upon the input slew and the output load. So somewhere if the input slew will be high, then in that case signal will take some time to reach the output. So we will discuss about this concept in upcoming sessions when we will discuss this slew concept and skew concept. Yeah. So yeah. So in this session we have started with the unitness concept, and Yeah, first we have started with timing arcs, cell arc, net arc, and we have also discussed about uniqueness, positive uniqueness, negative uniqueness, and non-unit. So yeah, so that's all for today's session. Thank you. So if you're having any particular doubts or queries, you can stay and ask me, or else we can end the session. Thank you.